Hello learners, we know the concept of rate of reaction, factors affecting rate of reaction, order and molecularity of the reaction. Today, we will discuss how to explain the concept of activation energy and how it relates to the variation of reaction rate with temperature. Interpret potential energy profiles and use them to determine the activation energy and potential energy changes for a reaction. Use the Arrhenius equation to calculate a rate constant, activation energy and frequency factor. Define a catalyst and describe the effect of a catalyst on the energy requirements for a reaction. We know that the rate of reaction depends on concentration of reactants or on pressure in case of gaseous reactants. Along with concentration or pressure of reactant, temperature also has a major effect on the rate of reaction. It has been observed that generally rate of reaction increases with increase in temperature. Also, it has been found that an increase of temperature by 10 degree nearly doubles the rate constant. The dependence of the rate of a chemical reaction on temperature can be accurately explained by Arrhenius equation. Arrhenius equation gives the relationship between rate constant K of a reaction and the absolute temperature T. It is defined as K equals to A multiplied by E raised to the power minus EA upon RT, where K is the rate constant and A is the Arrhenius factor or the frequency factor or pre-exponential factor which is constant to a particular reaction. EA is the activation energy, R is the gas constant and T is the absolute temperature. To understand this better, let us consider a reaction between hydrogen and iodine to form hydrogen iodide. H2 combining with I2 to form 2HI. According to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. The energy required to form this intermediate is known as activation energy. If we plot the potential energy of the molecules versus the reaction coordinate, we get the curved shape. The peak of the curve is the transition or the intermediate state, which is also known as activated complex. The energy required by the reactant molecule to form this intermediate called activated complex is known as activation energy, or in other words, this is the minimum energy required to cause the reaction. Even though the reaction is spontaneous, that is, delta G is negative, the reactant molecule still needs to go through the transition phase in order to react. Some energy is released when the complex decomposes to form products. So, the final heat of the reaction depends on the nature of reactants and products. All the molecules in the reacting species do not have the same kinetic energy. To overcome this problem, Maxwell and Boltzmann used statistics to predict the behavior of large number of molecules. They plotted the fraction of molecules Ne upon Nt with a given kinetic energy E versus kinetic energy. The peak of the curve corresponds to the most probable kinetic energy, that is, kinetic energy of maximum fraction of molecules. Only those molecules which have energy more than activation energy EA can take part in the reaction. When the temperature is raised, the maximum of the curve moves to the higher energy value and the curve broadens out, that is, spreads to the right. As a result, large number of molecules will have higher energy. The area under the curve T and T plus 10 is same. Increasing the temperature of the substance increases the fraction of molecules which collide with energies greater than EA. It is clear from the graph that in the curve at T plus 10, the area showing the fraction of molecules having energy equal to or greater than activation energy gets doubled, leading to doubling the rate of a reaction. In the Arrhenius equation, K equals to A multiplied by E raised to the power minus EA upon RT. The factor E raised to the power minus EA upon RT corresponds to the fraction of molecules that have kinetic energy greater than EA. Taking natural log of both sides of Arrhenius equation, we get log K to the base E equals to minus EA divided by RT plus log A to the base E. Let this be equation 1. If we plot log K to the base E versus 1 by T, we get a straight line with slope equal to minus EA upon R and the y-intercept as log A to the base E. From the graph, we can see that increasing the temperature or decreasing the activation energy will result in an increase in the rate of the reaction and an exponential increase in the rate constant. As log to the base E is equal to 2.303 log to the base 10, equation 1 can also be written as 2.303 multiplied by log K to the base 10 equals to minus EA upon RT plus 2.303 multiplied by log A to the base 10. On dividing this equation on both the sides by 2.303, we get log K equals to minus EA upon 2.303 multiplied by R multiplied by T plus log A to the base 10. Let this be equation 2. At temperature T1, equation 2 becomes log K1 to the base 10 equals to minus EA upon 2.303 multiplied by R multiplied by T1 plus log A to the base 10. And at temperature T2, equation 2 can be written as log K2 to the base 10 equals to minus EA upon 2.303 multiplied by R multiplied by T2 plus log A to the base 10. Let these equations be 2A and 2B respectively. On subtracting 2B from 2A, we get log K2 to the base 10 minus log K1 to the base 10 equals to EA upon 2.303 multiplied by R multiplied by T1 minus EA upon 2.303 multiplied by R multiplied by T2, or log K2 upon K1 to the base 10 equals to EA upon 2.303 multiplied by R multiplied by 1 upon T1 minus 1 upon T2. Thus, Arrhenius equation can be used to calculate activation energy at different temperatures if the experimental value of rate constants are known. By now, we are aware that rate of reaction depends on the concentration of reactants and the temperature. Along with concentration and temperature, a catalyst also has a major effect on rate of reaction. A catalyst is a substance which alters the rate of reaction without itself undergoing any permanent chemical change. A catalyst enhances the rate of reaction. Let us have an experience on how does catalyst affect the rate of reaction by performing an activity. I have taken 25 ml of hydrogen peroxide in the two flasks. Do we see any kind of gas being released by decomposition of hydrogen peroxide? Nothing seems to be happening to the hydrogen peroxide. Add black powder of MnO2 gradually to one of the flasks containing hydrogen peroxide. What difference do you observe in both the flasks? Oxygen gas is evolved and the effervescence can be seen in the flask in which MnO2 was added, whereas still no gas is evolved in the flask having only hydrogen peroxide. Why did this happen? MnO2 behaves as a catalyst here to increase the rate of decomposition reaction of hydrogen peroxide into water and oxygen. The action of the catalyst can be explained by intermediate complex theory. It is believed that the catalyst provides an alternate pathway for reaction mechanism by reducing the activation energy between reactants and products and hence lowering the potential energy barrier. As a result, large number of particles are capable of forming products, thus increasing the rate of reaction. A small amount of the catalyst can catalyze a large amount of reactants. It is also found that catalyst does not change the equilibrium constant of a reaction. Rather, it helps in attaining the equilibrium faster. Now let us arrive at the modified Arrhenius equation on the basis of collision theory of chemical reactions. It explains how chemical reactions occur. According to this theory, chemical reactions occur when hard spherical molecules of the reactant collide with each other. Also, the reactant particles must collide not only with sufficient activation energy but also in correct orientation. The rate constant for a simple bimolecular reaction as predicted by collision theory is rate equals to P multiplied by ZAB multiplied by e raised to the power minus EA upon RT, where P refers to the collision between molecules with proper orientation, ZAB represents the collision frequency of reactants A and B, and e raised to the power minus EA upon RT represents the fraction of molecules with energies equal to or greater than EA. The Z in this equation can be compared to A in Arrhenius equation. Thus, in collision theory, activation energy and proper orientation of the molecules together determine the criteria for an effective collision and hence the rate of a chemical reaction. We have arrived to the conclusion that the minimum extra energy absorbed by the reactant molecules so that their energy becomes equal to threshold energy is called as activation energy. Lower the activation energy, faster is the rate of reaction. Presence of a catalyst lowers the activation energy barrier and hence the reaction becomes faster. Activation energy and proper orientation of the colliding reactant molecules together determine the criteria for an effective collision. Now let's take up few questions. Question 1. The rate of the chemical reaction doubles for an increase of 10 Kelvin in absolute temperature from 298 Kelvin. Calculate activation energy EA. Question 2. The activation energy for the reaction 2HI giving H2 plus I2 is 209.5 kilojoules per mole at 581 Kelvin. Calculate the fraction of molecules of reactants having energy equal to or greater than activation energy. Question 3. The decomposition of A into product has value of K as 4.5 multiplied by 10 raised to the power 3 per second at 10 degrees Celsius and energy of activation 60 kilojoules per mole. At what temperature would K be 1.5 multiplied by 10 raised to the power 4 per second? Keep practicing and keep learning. Thank you.